All right, so this, let me give you a little bit of background on this. This is my daughter, Isabella Winter. She's been coding for 4 years. If you like what you see here, all of the slides and all of the background information and stuff can be downloaded from this website. This is her code name, Lambda. And I'd like to give a quick overview of what we're going to go through today. So what we want to do is build logic circuits, like computer engineering kinds of stuff, AND gates, OR gates, ripple adders, that kind of stuff in Minecraft. And we assume, and this is probably not the right kind of assumption for this audience, but we assume that people have no previous background in Minecraft. So we're going to give you through, for the sake of completeness, we're going to tell people, this is how you create a world that's redstone ready and stuff like this. We're going to talk a little bit about how you simulate current in Minecraft. And then we're going to go through these 3 lesson plans. One to do basic logic gates, structure blocks. It's still hard to hear? Wow, okay. I feel really loud up here. Okay, all right. Okay, can you hear me now? All right, so we're going to do this. We're going to do basic logic gates. We'll go through that kind of quickly. We're going to talk about structure blocks as a way to create abstractions in Minecraft. Abstractions are really, really important in computer science. Then we're going to do parts of an ALU, arithmetic logic unit. And then if we have time, we'll get into memory, how to implement memory in Minecraft. The idea ultimately is that in theory, you could actually build a working computer in Minecraft itself. And I think on that, I'm going to turn over the floor to Bella, and we'll be team tagging and passing the microphone back and forth during this talk.
Okay, so we're going to talk about how to make a redstone ready world. So you want to go to single player and then create a new world, creative mode, more world options, and then you want cheats on, and then you want a super flat world customized to redstone ready. So that will create a super flat sandstone world. So here's a picture of it, redstone ready virtual makerspace. So now we're going to talk a little bit about redstone or simulating current in Minecraft. So in this talk, the power components we're going to use are levers and redstone torches. So, redstone dust is pretty much the Minecraft equivalent of wire, but it can only transmit so far without the use of a repeater. So the signal can only transmit 15 blocks without a repeater. And then here's a repeater. It will boost the redstone signal back to full strength and allow it to continue going. So then the mechanism component we are going to use is the sticky piston, which is very similar to a piston, but instead of just pushing blocks, it can also pull blocks. So then we're going to talk about opaque blocks. So these are blocks where you can send a signal through them, but they're only weakly powered even when a signal is going into them, so you will need a repeater to recharge the signal after going through an opaque block. So now we're going to talk a little bit about basic logic gates, the NOT, OR, AND XOR gates.
And I'd like to just jump in here really quickly. The motivation for doing this came from this crash course series on YouTube called Crash Course in Computer Science, which is awesome. If you have not seen it, it's awesome. And this is video 3, so this is a link to that video.
Yeah, they talk about how the logic tables and how they created gates like this in actual computers. So the NOT gate just takes the input and takes the opposite. If the input's a 0, the output's a 1, and if the input's a 1, the output's a 0. And I've actually seen this one editor where it doesn't call it a NOT gate, it calls it an inverter. So for a NOT gate, you're going to need a lever, redstone dust, an opaque block, and a redstone torch. So there's this special case with a redstone torch where if you send current into the block that it is on, then it will turn off that torch. So this Here is if you have 0 as an input, you get this 1 as an output. And if you get a 1 as an input, you have a 0 as an output. So then now we're gonna talk about the OR gate. So if any of the inputs are 1, then the output will be a 1. So 0 and 0 as an input, we get 0 as an output. 0 and 1, we get 1 as an output. 1 and 0, we get 1 as an output. And 1 and 1, we get 1 as an output. So then for the OR gate, this one's just a lever and redstone dust. So this one is pretty simple. It takes advantage that redstone dust next to each other just kind of pulls together into a single wire. So here's the OR gate with 0 and 0 as an input. Here's it with a 1 and a 0. Here is with a 0 and a 1, and here's with a 1 and a 1. So now we're going to talk about the AND gate. So with this one, all of its inputs have to be 1 in order for the output to be a 1. So we have 0 and 0 as an input, we have 0 as an output, we have 0 and 1 as an input, we have 0 as an output, we have 1 and 0 as an input, we have 0 as an output, and we have 1 and 1 as an input, we get 1 as an output. So for the AND gate, you're going to need a lever, redstone dust, an opaque block, a sticky piston, and a repeater. So this is what the AND gate looks like in Minecraft. So this is with 0 and 0 as an input, and over here we have 0 as an output. Here the opaque block is in the correct space, but there's no signal to travel through it. Here there's current that could go through an opaque block, but there's no opaque block there. And here the opaque block is in the correct space and there's current to travel through it. So now we're going to talk about the XOR gates logic table. So one way to look at this is if you're at a restaurant and you have a sandwich and you can have it with a salad or a soup, they don't mean you can have both a salad and a soup or one or the other. They mean you can have a salad or a soup, but not both. So this is kind of like that. So a 0 and a 0 as an input, we have 0 as an output. We have a 0 and a 1 as an input, we get a 1 as an output. We get a 1 and a 0 as an input, we have 1 as an output. And 1 and 1 as inputs, we have 0 as an output. Another way to look at this is if you have an even number of zeros or an even number of ones going into the gate, then it will be off. And if there are an odd number of ones, then it will be on. So you can actually build these XOR gates with other gates, with the OR gate, the AND gate, and the NOT gate. So both of these are functional versions of the XOR gate. This is how I built it, but you could debate that the AND gate is the hardest gate to build, so maybe this is easier. Either way, they both have the same functionality. So now we're going to do a quick demo of this in Minecraft. So, oh, nope. So we're just going to go to Minecraft here, and I'm just going to go, this is my redstone world here where I have a bunch of my computer creations. So I'm just going to go over to the logic gates. So right here is an AND gate. So here's an AND gate with the top cut off. So this is just the same thing as in the slides, but it has this case around it. That way the redstone doesn't just become one big wire. So this is just an AND gate here. And then over here we have an OR gate. So this is just the same thing as in the slides. And then here's the XOR gate, and you will notice it is a lot bigger than the AND gate and the OR gate. That is because it is made up of other logic gates. So this is a lot bigger. So you can see that if I turn one of them one of the inputs on, then this redstone lamp will turn on. You see it's brighter now. But if I turn both of the inputs on, this is darker now. So as I'm sure many of you know, if you have this bright red, then that is active, and this dark red is inactive. And here we have just a little NOT gate, so if we turn this on, then this will turn off. So that's nice and functional. So we're just going to go back to the slides. So now we're going to talk about structure blocks. So they are essentially the way you abstract your structures in Minecraft. So here is a little bit of text about structure blocks. And then obtaining a structure block, you need cheats. So you want cheats in that world, but you want /give at p structure block. So this will give you a structure block. And then they talk about structure blocks at this link. So this is a little, just a little demo of structure blocks. So you see we have the structure name is AND gate, and then we want to load the structure. So it's just a little demo of what the interface looks like. So you want to create a structure block entry. You want to create a structure for each of these 4 logic gates. So now we're going to talk about making a partial ALU. So we have a
So let me jump in. The reason why you want to create that structure, that level of abstraction, is because now we're going to use those as single ideas to build more complicated things from those.
Specifically with the XOR gate, we don't want to have to rebuild that every single time when we want to use an XOR gate. So with the partial ALU, we're going to talk about building a half adder, a full adder, and a 4-bit ripple carry adder. So the half adder will take 2 single-digit binary numbers and add them together. So if we have, here's the table for the half adder. So we have 0 plus 0 as an input. We have 0 in the 2's place and 0 in the 1's place. 0 plus 1 is a 1 or just 1. And then 1 plus 0, same thing. And 1 plus 1 is 1, 0, or 2. So it turns out you can create this with an XOR gate and an AND gate. And I'm not sure if you can see the wires here, but there are some connecting wires there. So we're just going to go through this real quick. So if we have 0 plus 0, the inputs to the 2 gates are 0. So the output is 0 in the 2's place and 0 in the 1's place. So then we have 0 plus 1. So 0 and 1 are the inputs to both the gates. So then we have a 1 in the 1's place and a 0 in the 2's place, or 1. That is correct. Then we have the same thing, but it's 1 plus 0. So that has the same output. And then if we have 1 plus 1, they should equal 1, 0, or 2. So with the XOR gate, 1 and 1 as an input is 0, and 1 and 1, and then AND gate is 1. So this works. So now I'm going to show you this in Minecraft. So I'm just going to go over here. So over here I have this half adder rigged up. So 0 plus 0 is 0, again using redstone lamps. We have 0 plus 1, that is 1. We have 1 plus 0, also 1, and 1 plus 1 is 1, 0. So that all works. I'm just going to turn this off. Okay. So now we're going to go back to the slides and talk about the full adder. So you want to create a structure block structure for the half adder because, yeah, so you can now use this as a single component. You don't have to rebuild this every single time you want to use a half adder. So now we're going to talk about the full adder. So you build this using 2 half adders and an OR gate. So the first two inputs feed into a half adder, and the ones digit of this goes into the second half adder along with the third 1-bit number you're adding. Now, okay, and the carry of this first half adder goes into this OR gate. So the second half adder, the sum of it goes into the ones place of the answer, and the carry of this goes into this OR gate, and then the result of this OR gate is the twos place or carry for the for our answer. So we want to abstract this into just a full adder. So we want to be able to use this as a single component. So now I'm going to show you this in Minecraft. Oh, nope. So over here, I have, yes, right here is our full adder. There we go. So anyway, we are going to 0 plus 0 plus 0 is 0, 0, or 0, which is correct. We have 0 plus 0 plus 1, which is 1, correct. We have 0 plus 1, which is 1, 0, or 2, which is also correct. And we have 1 plus 1, which is 1, 1, which would be 3. So that is also correct. So if you see here, here's a full adder, and you see it has these white lines around it right here. So this indicates that it is a structure from a structure block, but you might notice that there are 2 structures here actually instead of 1, and this is because the structure blocks have limitations, and they cannot. Any given structure can only be so big. So for this, I have a first structure and a second structure for my full adder. So I'm just gonna go here. So we are going to go back to the slides. So then there's a 4-bit ripple adder. So a 4-bit ripple adder will take 2 4-bit numbers and add them together. So what you want to do is, so we have A and B as our 2 4-bit numbers. So the first digit of A, the ones digit of A and the ones digit of B, we're going to feed those into a half adder and add those together. So the ones digit of that becomes the ones digit of the our answer, and the carry of that feeds into this full adder, and that full adder will add the carry of this last one plus the twos digit of A and the twos digit of B. So we're going to add those together, and the sum of that, or the ones place, will become the twos digit for our result, and then the carry of that will feed into this next full adder, and that just continues on going. Similarly, here's the 3rd digit, and here's the 4th digit, and then on the last one, the carry is just the 16th place. And you may notice that in the crash course videos, they actually do a 8-bit ripple adder instead of a 4-bit ripple adder. But in Minecraft, this is a very large machine already, so I did a 4-bit one to make it smaller. So we're going to go to Minecraft, and yeah. So here is our 4-bit ripple adder. So it is a very, very big machine. So here's our first half adder, here's our full adder, here's another full adder, and here's another full adder, and then we have our result down there. So over here we have the input. So right here I just have 14 plus 14, or 1110 plus 1110. So I have this input into the lever, so I have these 3 on and this one off. and then these 3 on and this one off. So this should be 28 or 11100. So I'm just going to fly over here. So this is already a very large machine, and a 8-bit ripple adder would be twice as large. So that's why I chose not to make an 8-bit ripple adder. So you can see over here I have these redstone lamps above these doorways. So over here I have this one's on, this one's on, this one's on, this one's off, and this one's off. So we have 11100 or 28, so that is working. And then I'm just going to teleport back to the regular. Okay. So I've just teleported back, and we're going to go back to the slides now. So then we're going to talk about memory. So we're going to talk about a gated latch, aka the flip-flop, and then we're going to talk about a partial RAM. So here's an OR gate, and if you have the OR gate's result loop back into one of its inputs and make one of the inputs 1, this will store a 1 forever, because this output will be 1 and it will loop back into the OR gate and it will be a 1 forever no matter what. So I mean, it's good, it's storing a 1, but the only issue is that this is permanent, so there's no way to change this. And then here's an AND gate rigged up the same way, but instead of storing a 1 forever, this will store a 0 forever. Again, the only problem with this is permanent. So then there's this AND or latch. It works, it's memory, so if you have, if you make the set input a 1, then it will set the output to a 1, and if you make reset a 1, then you will set the output back to a 0, and if neither of them are 1, then it will just store whatever was last put in it, so it's functional. So we have 1 as the reset, and then if we have, so B is what we have currently stored in there. So we have the set is 1, so this is 1. And then we have a NOT gate over here, right here. So then this will store a 1. And then it will just store B here, so this is B, because if B is 1, then this output will be 1, and if B is 0, then this output will be 0. So this will effectively store whatever was last put in it. But it is a little confusing to have a set and a reset, so we can fix this by adding a few more gates. So this is a flip-flop. So this has a data wire and a right enable wire. So the right enable wire enables you to change the value that is stored in there, and the data wire, if the right enable wire is on, then whatever's on the data wire will be what's stored. So yeah, we have right enable is 0, this is all 0, and it will store B. If right enable is 1 and data is 0, then this will effectively store, so you see this output will be 1, but there's a NOT gate there. The output of this will be 1, but there's a NOT gate right here. So this will effectively store a 0 because there's a 0 on the data wire. And then if we have a 1 on the data wire and a 1 in the right enable, this should store a 1. So we have 1 up there, so that becomes 1. So this is 1, which is good. And then this will be a 0 and a 1, so this output will be 0, but this is a NOT gate, so this will convert it to a 1. And then now it's storing a 1, which is good. So now I'm going to show you this in Minecraft. So I'm just going to go over here. So I have one of these rigged up. So this, again, redstone lamp is going to show the output. So instead of data here, I called it vals, so they're pretty similar. So then I have a gate latch memory, and a gated latch memory is another name for the flip-flop. So here's write enable. So right now what's storing is 0. We can toggle the data / value wire as much as we want. Nothing's going to change as long as write enable is off. So if we turn write enable on and then turn the data wire on, now it has a 1 as an output. Let's turn write enable off, and again, we can toggle this as much as we want, and it's not going to change. Now let's store a 0 again. Here we go. Again, toggle it as much as we want, no change. So this is effective. So you want to create a structure for this so that you don't have to rebuild this every single time you want to use it. So then there's a version of this that you can use for RAM. So what you want to do essentially in RAM is you have this grid, and you have redstone wires running down the columns and redstone wires running down the rows. And whatever little gated latch for RAM is at the intersection of those, that's the only one you want to store the value. So that you don't oh, I want to store a 1 in this single location and then store a 1 in the entire RAM. That wouldn't be a very effective RAM. So then you also notice there's this little star by output. So in the crash course videos, they have a single input-output wire, but here we split that in 2 because the repeaters are unidirectional. So that's why we have 2 wires as opposed to 1. So here we have an AND gate. So we have X and Z. So usually in a plane you hear X and Y, but I'm doing X and Z because So I'm doing X and Z for my columns and rows. So we don't want the write enable to work or the read enable to work unless it's the intersection. The data wire doesn't really need to be hooked up to that because it's not going to change anything as long as the write enable wire is not on. And then the output is reliant on the read enable wire, and the read enable is reliant on the coordinate. So that's fine. So here we have a write enable. So if it's the correct coordinate and write enable is on, then you can save whatever's on the data wire. Okay. So then you can save whatever's on the data wire, and then this read enable wire, if it's the correct coordinate and read enable is on, then you can take whatever's saved in this gated latch, and it will run to the output wire, which is nice. So you want to create, here's our gated latch for RAM abstraction. So we're just going to do a quick view of this in Minecraft. Here. So you can see over here I have a lot of trial and error. So here's some machines that did not work correctly. So over here we have this gated latch for RAM. So here we have the read enable wire, here we have the write enable, here we have the X and Z wire, the input and the output wire. So let's see. Nothing works really without these 2 being on. So it is the intersection for now, let's say. So then we have write enable. We don't actually. So let's see what's stored in there right now. So we turn read enable on, and it says 0. So if we turn write enable on and then the input to 1, we've now saved a 1. And so let's turn read enable off. Now this is off, so this is nice and functional. And nothing really works if it's not the intersection, which is good. That's what we want it to do. So then, okay, we're gonna go back to the slides. So here is a RAM. It's a 4x4 RAM, so a multiplexer. If we have enough time, I will show you how to make those in Minecraft too. But essentially what they do is they select the correct column or row, and then you have a single output wire for the entire grid, a single data wire, and a single write enable and a single read enable wire. So yes, because the output for all the gated latch for RAMs, those are all going to be hooked up to the output wire. The data wire for all of them is going to be all hooked up to the data wire. The write enable is going to be hooked up to the write enable, and all the read enables are going to be hooked up to the read enable, because the multiplexers will take care of selecting the right row. So I believe that that is all the time we have right now. So yeah, that's it.
And so all of this stuff will be at that lambda.bricklayer.org website, and we can even share the world with you if you want. Just send us an email or something if you're interested. Thanks a lot.
Thanks for doing this. Sorry to take you off.
That's okay.